Hey everybody, welcome to Bill Sky, the assembly guy. And what we're going to do today is we're going to go over stack frames on ARM processors like Raspberry Pi or like the Mac M1, M2 chip. And stack frames are a way to be able to implement nested functions, recursive functions, and I'm actually going to show some of those in a follow-on video. But stack frames are quite important, and I think the best way to do it is to just get into it. We're going to have some lecture, then we're going to look at code, a little more lecture, look at code, a little more lecture, look at code. And this isn't going to be a short video because stack frames are quite complicated. Actually, they're really not that complicated, but when you're first learning them, they can be very challenging. So I'm going to do my absolute best to describe them to you. I previously did an Intel x86-64 stack frame presentation. Wouldn't be a bad idea for you to take a look at that as well, because we have multiple different processor family groups out there, and you really should learn them all. So let's get to it. Okay, so ARM stack frames, what's it all about? So a stack frame is a data structure. A stack is a data structure which is used by the CPU as a temporary memory storage location. It's used heavily by functions. It's used to back up registers. It's used to back up pointers, addresses, things like that. And then you can grab them later on when you need them. And they don't take up registers. Now, if we had an unlimited number of CPU registers, we wouldn't really need to use the stack so much. We would still need the stack, but we wouldn't really need to use it that much. Other than functions. Functions is a really heavy user of the stack. And when you create an application, or when your application begins, it's automatically given some stack space. And just as a reminder, let's again go over what the stack is. So as you can see here, first of all, a stack is a first in, last out, or last in, first out data structure. And as you can see here, we have a stack. Those looks like a bunch of plates, blue plates. And there's a stack pointer that's sitting there which has the address of hexadecimal 200 in it. So that stack pointer always points to the top of the stack. And as you add things to the stack, the address of the stack pointer goes down. So what we're going to do here is we're going to subtract 16 from the stack pointer, and then we're going to store the X1 register contents into that location onto the stack. Now you might wonder, why are we changing the stack pointer by 16? Because in a 64-bit ARM program, the stack is 64 bytes wide, not 8. I'm sorry, 64 bytes. Sorry about that. I meant 16 bytes. It's 16 bytes wide, not 8, but 16. In a 32-bit ARM application, the stack is 8 bytes wide, not 4. So it's like double the size of the CPU register. And they do that because of the way that they process functions, and it always has to be aligned on a 16-byte boundary. So what we do is we subtract 16 bytes from the stack pointer, and then that will move the stack pointer up, which gives us space to put X1 into there, and you can see that right there. So hexadecimal 200, we subtract 16, it becomes hexadecimal 1F0, and then we're able to store the register X1 in that location in the stack. And you can see now on this screen, I said 16 bytes wide, so the stack is 16 bytes wide. Now you may say to yourself, well, aren't we wasting a lot of space on the stack if the register only is 8 bytes, if the addressing is only 8 bytes? We're using up 16 bytes? I completely agree with you. And I've seen some people not use the 16 bytes, but boy, I hear all the architects talking about warning you don't want to do that. So we're going to go ahead and, because memory's cheap these days, we're going to go ahead and use 16 bytes for every one. And so as you keep adding things to the stack, it keeps reducing by 16 bytes per entry, since the stack is 8 bytes wide. Actually, the stack is 16 bytes wide, not 8, except for 32-bit systems, it's 8 bytes wide. So that's a little bit of a typo on the screen. It should say on the third line, since the stack is 16 bytes wide. So if we want to now back up or copy X2 to the stack, we subtract another 16 from the stack, we store X2 to the stack, and you can see how the stack pointer's address has now gone from 1F0 to 1E0, and it's now stored X2 there. We can add a third one, There's x3. Notice the stack pointer address has gone down. So that's how you add things to the stack on an ARM processor. Now, there's this command in x86-64 Intel, which is simply push. Guess what the push operation does in that operating system? It subtracts, in that case, it would subtract 8 bytes from the stack pointer and then put the value on there. So it's one statement less, and you'll see a lot of that when you compare x86-64 and ARM. But that's one thing that makes ARM a little bit faster, is that you might have more code, but it uses up less memory. It actually runs faster. So as you pop things off the stack, you grab the data from the stack pointer. In this case, we're going to load the register X0 with the value that SP is pointing to, which is the old X3 value. Now over there on the right, you see X3, X2, X1. Those aren't actually stored on the stack. It's the value that happened to be in those registers. So I just have the X3, X2, X1 so we can keep track. So you load the data from the stack using the dereference stack pointer with the square brackets, and then you increase the stack pointer by adding 16. And so now in this line, in this one right here, the value that was in X3, which is now in the stack, is copied to the X0 register, and then it goes down one stack entry. And so then what we're going to do is we're going to load X2, because you notice how the stack pointer is now pointing to the X2 value. We're going to load X2 into 0, add 16, then we're going to load the X1 value into X0 and add 16. So that now where the stack is back to where it was before we started adding things to it. But one thing I do want to tell you here, notice how the data is still on the stack. When you pop something out of the stack, it doesn't actually remove it. So that could be a problem when you're dealing with passwords or, I don't know, social security numbers or anything that you might push on the stack. You want to clear off the stack by zeroing it out or whatever, so you don't have a security issue. And my IT brain seems to remind me that a lot of security problems happen because data is not cleared out of memory, and then hackers find out about it and they're able to grab that information, especially if it's like a password or something. So you want to zero out the stack before you actually pop it, and we're going to show you a demonstration of that. So what is a stack frame? So that was the overview. That was a reminder of how the stack works in an ARM processor. What is a stack frame? A stack frame is a subset of the stack which your program is allowed to use. If you notice right here, my program can use, from the frame pointer on the bottom, it has the use of all of that stack area. And that is called the stack frame, where you have the frame pre-pointer on the bottom. In x86-64, they call that the base pointer. But you have the frame pointer on the bottom, and then your stack pointer moves up and down as you add and remove things from the stack. And again, this subset of the stack is called the stack frame. It's defined by the frame pointer, which is FP or X29 at the bottom of the stack, and then the stack pointer, which is at the top of the stack, which is the SP register. Now here's a good example of a substack of a stack frame, which is a subset of the full stack. You can see that all of the entries below the frame pointer belong to some other process. Like, let's say the main function that's calling your function. And your function owns the frame pointer up to the stack pointer. So it owns 2 entries in the stack. However, the main program looks like it owns 4 entries. So when you call your function, what you need to do is you need to store the return address into the stack. That's the first thing that you do. So you take whatever the line of code, the address of the line of code below your call, you save that into the stack, and then you save some other things. You might have arguments to the function that you're sending to the function. Those go onto the stack. The stack also is used to contain local variables. We're going to take a look at all of that. We're actually going to do some programming. So why go through all of this? Well, what if you want to recurse a function 500 times? Well, you don't have 500 registers. So you've got to use some kind of a data structure to actually do that, and the stack is perfect for that. So recursive functions, nested functions are like recursive functions. Every recursive function is a nested function, but not every nested function is a recursive function. but they're basically the same thing. A function that calls another function is a nested function, or a function that calls itself is a recursive function. And using the stack for arguments and local variables, you don't need to use registers, so that really eliminates the need to use up all of your registers. Even though ARM has a whole lot more registers than x86 64, there's just aren't enough. And since the CPU doesn't have that unlimited number of registers, we have to use something else, and that's why we use a stack frame. So let's start talking about what is the process when the operating system actually calls a function. How does the CPU actually do that? So the stack contains data from many different processes. It might contain data from your main function, other functions that are called by your main. The stack also has information from other completely separate processes. So when a function is called, the function needs to define its portion of the stack it will use. That's called the stack frame, and the way that it defines that is it sets up the frame pointer and then the stack pointer. And then when the function ends, the stack frame must be destroyed by the function right before the function ends. We're going to look at all of that. So let's get to an actual example. So before a function is called, the stack contains data from functions within the current process. In this case, I don't think we've got any functions that our main has called, but it has put some data into the stack. Notice that it put the x0 register value, it put some data. And notice how our main function, its frame pointer, has an address of 200, and the stack pointer is 2 entries above that with an address of 1E0. Now the address of the one right below that would be 1F0 and then 200. Remember, the stack pointer always goes down as you add things to the stack. So that stack has some stuff in it. Now each function must have a base where it cannot move below the frame pointer. So in other words, if this is our main stack, the main function cannot go below the frame pointer. Like for instance, it shouldn't go and modify data at position 210. That would be illegal. Now it might be able to access data below there, and you're going to see why we might have to do that. But in this case, let's just say it shouldn't go below there. So each function has a base where it cannot move below. That's called the frame pointer. And each function has a top of the current stack, and that's called the stack pointer. So when you call a function, the address of the line of code below the call, which is the return address when the function is done, it is not placed automatically onto the stack like it is in x86 64 Intel. So you have to do that. That's one of the first things you have to do within your function is you have to store that line, that return line of code address into the stack so it's not lost. Now, that address is actually stored in a register, which you're going to see in just a moment. So as you see right here, the program counter, which is the instruction pointer, it's pointing to the branch link some function statement, and on the left you'll see the address of that statement, and the statement right below that is a no-op, and you'll see the address of that statement right to the left. Now those address numbers might not be perfect, but they show you how the address goes up as you go down the lines in your code. So I've got those two lines of code on this new screen up on top. So when you say branch link to some function, what actually happens? Well, the program counter, and I said here the instruction pointer, that's from x86 64, but they're basically the same thing. The program counter in ARM, the contents of the program counter is changed. What goes into the program counter? The address of the first line of code of the sum function. And you can see that happens to be the address 98345. So that number is actually put in the program counter. That's how the CPU knows to go to that memory and start executing code there. That's what the branch link does. The branch link does one other thing. It also stores the address of the line right below the branch link, which is the no-op 12349. It actually stores that address into the link register. So we have got to save that address so we can return correctly from the function. So to do that, the first thing you do to create your stack frame is you add space in the stack. So we're going to subtract 16 from the stack pointer, and then we store the link register into the stack pointer. So as you can see here, the stack pointer has moved up, and the link register, in this case it has the value 12349, that's stored in the stack. That is the return address when you're done with the function, you're going to return to that address. And I'm going to go back here. That address is that no-op, is that 12349, that no-op right before the branch link. So now we have saved the return address. And the x86-64, as I mentioned here, does it for you. The call function will actually do that for you, but it doesn't do that in ARM. So that's the first thing you do. You just have to save the return address of your program. So once you get that return address stored in the stack, now what you have to do is you have to back up the old frame pointer. And why do we have to back up the old frame pointer? Because the program or the function that called us needs to know where its bottom is, right? It's not going to remember. So we have to store that frame pointer for the old function, the function that called us. We have to store that in the stack. So what we're going to do is we're going to subtract 16 from the stack pointer again. We're going to store the FP, the frame pointer, into the dereferenced stack pointer. And you can see it right there. You can see that the frame pointer on the bottom has an address of 200. We're going to store that into the stack. And you can see how the stack pointer has reduced in size by 16 bytes or hexadecimal 10 yet again. So now we have saved all the data that we need before we return. And what's the next thing we have to do? We have to now move the frame pointer up. So we have to move it up to the same level as the stack pointer, so our function knows where the bottom of its stack frame is, knows where it's not supposed to go below. So what we do is we simply move into the frame pointer the address of the stack pointer. And you see it right there. So now the frame pointer has moved up. It's at the same level as the stack pointer. Now my stack pointer can move up and down as I add things to the stack, and that frame pointer never stops. That's the base of our stack frame for our function. And we're really not allowed to go below that. So now your function can use the stack frame starting at the frame pointer, which is the new bottom of the stack, continuing to the maximum size of the stack. So you can use as much of the stack in your function as you need. We have that frame pointer, you're not allowed to go by there. So what we're going to do here is we're going to subtract 16 from the stack pointer. We're going to go ahead and store x2 into the stack pointer dereferenced, and you can see the x2 value there. Our stack pointer moves up. Let's do it again. This time let's save x1 into the stack pointer. After we subtract 16 from it, you can see how x2 is there. Now that is the growing stack frame that our function is allowed to use. Now, how do we get rid of the stack frame? Well, what you do is right before your function is finished, you must move that stack pointer back down to the frame pointer. We're basically going backwards. Now, what you could do is you could do a lot of subtract. So I could add 16 to the stack pointer, then add 16 again, or I could just move the frame pointer value into the stack pointer, and voila, the stack pointer is now back at the same level as the frame pointer. But one thing I want you to notice is that those values from the x1 and x2 registers are still in the stack. You might want to get rid of those. Okay, what do we have to do after that? After that, what we have to do is we have to pull that 200. We have to pull that address that we backed up, which was the parent or the calling function's frame pointer value. We have to copy that back into the frame pointer so it goes back down where it belongs before our function leaves. And the way that you do that is you load register frame pointer from the dereferenced stack pointer. That will put 200 into the frame pointer again, and then you add 16 so the stack pointer moves down, and boom, there it is. So now our frame pointer is now back to the base where it was before the function was called. Now, when your function issued the branch link, what it did was the return address of the line below the branch link, which was that no-op, that address was put in the X30 register or the link register. So what we now need to do is we need to put that 12349, we need to put that address back into the link register before we return, because the return is going to use the X30 register to know where to go back in the main function. So what we're going to do is we're going to load into the link register. You could also say X30, but we're going to load into LR the dereferenced stack pointer, which would put 12349 back into the X30 register. Then we're going to add 16 to the stack pointer so it moves down. Now when you do a return, what it's going to do is it's going to grab the address that we just restored into the X30 register. It's going to grab that, put that into the program counter, and now the program is back. The program counter is now pointing to the line of code right below the sum function. We still have a lot of data up there into the stack. It might have been a good idea to zero that out. Now before the demo, I would recommend, if I lost you anytime during that lecture, stop the video, go back and redo it. And one way that I have learned to understand things like that is to have a piece of paper out and draw as the teacher is talking and try to work it out yourself, figure it out. You might have to watch that part of the video 2 or 3 times to really understand it, but this coding demo should really help. So let's get to some ARM coding. All right, some program. Let's get into this coding. All right, so I simply have a 64-bit ARM assembly language program here. And what I'm going to do is, just because there's a lot involved here, I'm going to put some, not branch lengths, I'm going to put some no-ops here. And then we're going to put some code in here. All right, so remember what we did was we did a branch link. So I'm going to say branch link, and let's create a function called sum function. And then we have a no-op right below it. I actually like putting no-ops right below this, and I'll remove those later on. But I just like to use no-ops all the time so the program will stop, it won't do anything new, and I can check things out. Okay, so there's my branch link. I'm going to build it, and we get an error because it doesn't know what sum function is. So let's go down here and create sum function. There's my sum function. I'm going to put a return right there. So now it should build. Now sum function doesn't do anything. It does absolutely nothing. And that's okay for right now. So let's go ahead and now this sum function is going to do really very little. And let's go ahead and just throw something together here. Let's first of all create our stack frame. Now one nice thing about stack frames is that they're always the same. So once you create your first stack frame, to create another function that has a stack frame, you basically just copy and paste. And then you add your function's content. So let's just go ahead and do that. So I'm going to create the stack frame. And it's always a good idea to comment these things so a new programmer doesn't look at it and say, what in the heck is that, right? If they see the comment there, they'll say, what is a stack frame? Then they'll look back at their old textbook or their notes and they'll figure it out. Okay, so what we have to do is we have to back up the link register. That is the address of the return line of code after some function is done. So I'm going to subtract from SP 16 bytes. So that's going to move the stack pointer up 1, and then I'm going to store your link register into the dereference SP. Now if I wanted to, I also could have done store X30 SP. Whatever way you want to do it. I like using the LR because I don't always memorize that X30 is the link register, so I just always use LR. Okay, so now we've backed up. That was step number 1. We backed up the link register. And that's really what we need to do here. Number 1, back up the link register. And you might want to say for returning from the function. All right, good comments really make your life easier as you code more and more. All right, so now let's go ahead and let's update let's back up the old frame pointer. Remember, we need to back up the bottom of the frame that the function who called us was using. So we're going to subtract from the stack pointer 16 more bytes, and this is number 2. Back up the old frame pointer, and we're going to store the frame pointer into SP. So the calling function can operate correctly. All right, that's it. That is the creation of our stack frame. Now let's destroy it. Our program is not going to do anything, so I'm going to put a no-op there, and I'm going to say let's destroy the stack frame. Now, by the way, there is a single line of code that will do all of this for you instead of 4 lines of code. There is one line of code. I'll be showing you that later in this presentation, this video. But for now, let's look at the longhand way because it might make it easier for you to understand. Okay, so what we want to do is we want to actually do the reverse now. So we want to actually take each one of these lines of code up here and just go backwards. So what does that mean? Is I'm going to load, actually I'm going to move into the SP, the frame pointer. So this is going to be put the, two slashes, reset the stack pointer to where it was before the call. Now I'm going to load the old frame pointer from the stack. That is the backup of the calling function's frame pointer. So restore the calling function's frame pointer from the stack. So after we put it on there, we now have to move the stack pointer down. So I'm going to say add stack pointer, hashtag 16, go to the next position in the stack. And actually, I think it should be the previous position. Whatever you understand. Go down one position. Okay. Now we need to recover the link register. Remember, the link register X30, that is the address, that will contain the address that return will use to go back to its position into the stack and into the program. And we're going to see that. We're going to demonstrate this. So I'm going to load into the link register the stack pointer, restore our return address, and then we're going to go to the next position of the stack, and I'm not going to type that in there. All right. That is our stack pointer, or that's our stack frame at the top. We create it, and our stack frame is destroyed on the bottom. Oh my goodness, I just completely missed, I forgot to make the frame pointer equal to the stack pointer. Oops. So one line of code when I was constructing the stack frame, I forgot to say move into the frame pointer, the stack pointer. Now bring the old frame pointer up to the stack pointer. I completely forgot to actually create the frame pointer. I forgot to move the frame pointer up to where it belonged. Oh my goodness. And I've got notes sitting here in front of me and I still got it wrong. All right. Now before we do this, I'm going to just run it and see no problems. We didn't have that strange error. So now let's go ahead and debug it. Okay, so main. I accidentally closed my tab. Whoops. All right, let's go. So now we're going to go into the function. We back up our link register, our return address. Now we back up our old frame pointer. It's now backed up. Now we move the stack pointer into the frame pointer to actually move that frame pointer up. And now let's go ahead and destroy things. So now we're going to put that frame pointer, now in the stack pointer. We're now going to load the old frame pointer. We're going to go to the next position in the stack. Now we're going to go ahead and recover the link register. And now watch what happens when we return. It's going to return to this no-op. That's what the return does. And guess what? We're at the no-op underneath the branch link statement, as you can see right here. So I'm going to just press continue and quit. So that is our basic function that contains a stack frame, and we destroy the stack frame. I have a no-op there to remind me that's where I have to put my code for my function. And believe it or not, C and C++ does it this way. So do other languages. They create a stack frame and then they put the code in. Now let's take a look at a stack frame that actually does something. Let's take a look at a function that actually does something. It's going to add a couple of numbers and it's going to return those numbers. So let's see how that all works. So for our function, to write a function that's going to add two numbers, we have to send those numbers to that function as arguments to the function. And to do that, we use the stack. So here's an example. So let's say we have a function that we want to send two numbers to it. We want to send the number that's in x0 and the number that's in x1. So what we have to do is we subtract 32 from the stack pointer. That's going to give us two positions in the stack. And then we store x0 at the stack pointer plus 16, and we store x1 in the stack pointer plus nothing. And when we do that, we get something like this. So if you notice, the x0 is 2 levels below the stack pointer, and x1 is right at the stack pointer. Actually, I should say x0 is 1 level below the stack pointer. And the stack pointer is pointing to the x1, and x1 is our second argument. So after we push those into the stack, after we push our arguments into the stack, then we call the function using the branch link. The branch link now is going to set up the stack frame. So it's going to subtract 16 from the stack pointer. It's going to save the link register. It's going to subtract 16 again. It's going to save the old frame pointer. And then it's going to set up the stack by moving the frame pointer up to where the stack pointer is. Now, I mentioned earlier that you can do this with a smaller amount of code. You can actually do this with a single line of code. That's the store pointer FP, or store, I don't even remember what STP stands for, but the STP, and what that'll do is it'll store the frame pointer and the link register to what stack pointer is pointing to, minus 32, and then the exclamation mark at the end will make that stack pointer address minus 32 be permanent in the stack pointer. And when you do that, you get this. So our stack pointer is completely set up. Now, it isn't one line of code. You have to do 2 lines of code, but we're actually going to do that in the coding demo for this. So now, here we go. So now your function, it has its stack pointer all set up, or it has its stack frame all set up. Stack pointer too. And what it needs to do is it needs to access the 2 arguments. Now, what it's going to do is to access the first argument, it has to grab the data where x0 is located, and the frame pointer, actually right now in this presentation, the frame pointer says it's x200. Let me fix that really quick. All right, now that I got that little typo fixed, let's now look at how to get the x0 value. We want to grab the x0 value. So what we're going to do is, since the frame pointer is our point of reference, that's where we're going to grab everything off of the stack. What we're going to do is we're going to load into x4. We're going to load register x4 with the frame pointer address, which is 1A0 plus 48. So we're going to take the frame pointer of 1A0, add 48. What is 48? 48 is 16 times 3, so that's 3 positions down. So it's going to go down to the LR, the x1, then the x0. So we're going to say load into x4, the frame pointer plus 48. Now it doesn't permanently change the frame pointer to frame pointer plus 48. If you want to do that, you put an exclamation mark on the right side of the square bracket after the 48. So we're not going to do that. But what that does is it puts that, in this case it was 100 hexadecimal, it puts that value that was in x0 as an argument, it put that into the x4 register. Now to grab the frame pointer, or to grab the second argument, you say load register x5. We're going to put the second argument into x5, and you say load register x5 frame pointer comma 32. Now I think there should be a hashtag in front of there. It depends upon the assembler you're using. But putting a hashtag in front of the 32, what that's going to do is that's going to go 32 bytes down from where the frame pointer is, which will be 2 positions in the stack, which means it puts x1 into x5, and there you go. So x1 had a value of 200 in it, so now x5 contains 200, x4 contains 100. And now you can add those 2 numbers together. The other thing you can do is you can also modify those arguments. You should really never do that. You should really never write anything below your frame pointer. It's very dangerous. You don't want to do that. But I could load into x0 999, and then I could store x0 into the frame pointer plus 32, and that puts 999 in that argument. Not a good idea to do that, but you could do that. Okay, so once the function is done, whatever it is, and we're going to do an add to function, but once the function is done, you destroy the stack pointer or the stack frame, just like we did earlier. Now our stack pointer is where it should be. Our frame pointer is where it should be. We want to move the stack pointer, though. We have to move it down 2 positions because we put 2 numbers in there as arguments. So to do that, you add 32 to the stack pointer, and now everything is back to where it was. But you still have a problem. You still have all that data up above the frame, up above the stack pointer. Let's zero that out. So before we completely leave our function, what I'm going to do is I'm going to move 0 to x0, and then I'm going to store x0 in 32 and x0 in 48. That zeroes out our arguments. That's if we want to zero out the arguments. And then we destroy the stack frame, and now we're back to where we were. Now, the reason that you have to do that, you have to do this last thing right here, where you have to add sp, hashtag 32. You do that in the main function. We're going to do that in the coding demo. The reason you have to do that is because you put 2 arguments onto the stack, you have to remove those. Whenever you put anything onto the stack, you have to remove it. So that will get the stack pointer down to where it belongs. So let's do a simple little add to function where we send 2 arguments to the function. It adds those 2 numbers, and it returns the result in x0. All right, we're back, this time with some more coding, and let's do that simple little add to function. So I'm actually going to put that, and really what I'm going to do is I'm just going to copy this sum function, because it already has all the code we need to create our stack frame, and I'm just going to say add to. Now, the reason that I do that is because I got the sum function working. That's my template for a stack frame function. I'm just going to go ahead and I'm going to just copy and paste it. Okay, so let's actually process the argument. So what's that going to look like? So I'm going to say branch link to add to, but before I do that, I have to push the arguments. And this is up in my main function. So what I'm going to do is I'm going to subtract sp, sp, hashtag 16, make room for my first argument, and then I'm going to store register x1 into sp. Store our first argument into the stack. Now I'm just going to copy and paste this. And actually, let's go ahead and make room for second argument. Let's change our comments. And let's put into x1. I don't know. You want to do 100? Let's try 100 there. All right, so that's going to put 100 as our first argument. Let's go ahead and now move into x1, 200. And if you remember in the presentation, after the function returns, it must add. Now, why do I add 32? Because each stack argument, each argument that I put in the stack is 16. I put in 2 arguments, so I need to add 32. 16 plus 16 is 32. I could have done this. It's a waste of a line of code, so I'm not going to do that. I'm just going to say 32. And I'm going to say clean up our arguments in the stack. Okay. Let's build that, make sure things are looking good. Okay. So now what we need to do is we actually need to go into our function and we called our function add2, we're going to go into our function and we're going to grab those 2 arguments and put them into a register to add them up. Now you might say, why don't we just put 100 into x1, put 200 into x2, and call the function, and then x2 or the function can then just grab them out of x1 and x2. That's a valid argument, but it's not the correct way to do it. You should always put arguments into the stack first, because what if you want to use x1 or x2 for something else, or what if the function does, right? By putting them in the stack, you're pretty much protecting them. Okay, so let's go ahead and I'm going to put another no op there. All right, so what I'm going to do is I'm going to load, and let's just say x4. I'm going to load into x4 my frame pointer 48. If you remember from our presentation, the first argument is always 48 bytes from the frame pointer. Grab our first argument. I'm going to put into x5, frame pointer, comma, 32. Our second argument, I'm going to clear out x0, and then I'm going to store. Actually, what am I doing here? I loaded. I need to add them together, don't I? So I'm going to say add x0, x4, x5. So add them together. I'm going to clear out, return register, add the 2 arguments. Now we have a little bit of a problem here, is that my function has used x4 and x5. So if the main was using x4 and x5, oops, we have a problem. So our function is overwriting x4 and x5. Bad function. You don't want a function to override registers that somebody else might be using. So we're going to back those up first. So I'm going to subtract sp kind of sp. So I'm going to make room for x4. And then I'm going to store x4 to sp. So we're backing up x4. Let's back up x5. So we're going to back up the registers that we're going to use. Back up x4 and x5. The registers we'll be using. Now, we have to restore those, don't we? So after we have done our addition, and before we destroy our stack frame, we have to restore those registers. So what we're going to do is we're going to go backwards. Okay? So I'm going to load register x5 sp. I'm then going to add sp comma sp comma pound 16. I'm going to load x4 sp. And I'm going to add sp comma sp comma hashtag 16. So let's restore x4 and x5 previously backed up. I hope all of you are really appreciating compilers, because this is what a compiler does for you. Also notice that these are done in the exact opposite. The restore is done in the exact opposite the backup was done. So I'm hoping to see this in the debugging. So let's go ahead and build this. All right, great. No errors. And x0 will contain our sum of x4 and x5. And if you remember, we added 100 and 200, so x0 should contain 300, and x4 and x5 should have the same values that they did before the function was called. That's why you want to do this. Now I'm going to comment out my branch local to some function because I'm not interested in testing that anymore. I know it works. So I just commented that out. I'm going to build it, and now let's debug it. Okay, here we go. Okay, so we're going to move 100 into x1. There's my 100. I'm now going to put x1 onto the stack. That's my first argument. Now I'm going to put 200 into x1 and put 200 onto the stack. And now I'm going to branch link to add 2. So now I'm going to add 2. So I create the stack frame. I'm now going to back up x4. Now let's take a look at x4 up here in the GDB debugger. It has a value of 0, and x5 also has a value of 0. So we're going to back up those two zeros. Now you don't know what those are going to have. In your function, you have no idea if they're supposed to be 0 or 100 or whatever. So we're just going to back those up to the stack, and there we go. So now we're going to load our first argument in x4. Look at our first argument of 100 is now in x4. We're going to load into x5 our second argument. 200 is in there. Awesome, this is working. And we're going to move 0 into x0. And then we're going to add x0 is equal to x4 plus x5. Let's scroll up and look at, yep, it's equal to 300. So our addition worked. Now let's see if our backup worked. So now we're going to restore x5. It now has the 0 that it had before the function began. x4 has the 0 that it had in it before the function began. We destroy our stack frame. And now we're back at the line below the branch link. And I wish I had put a no-op there. I didn't. I did. I have the add SP. So now we get rid of our two arguments because we add 16 twice to SP, which is 32. And now our arguments are gone. X0, it has the sum of 100 plus 200. Awesome. All of our registers are back to the way they were before the function was called. And our program absolutely worked correctly by obtaining arguments from the main function. Now let's take a look at creating temporary variables inside of a function. We're going to actually create variables in a function and then use those variables to do whatever our function needs to do. All right, let's take a look at how you would create local variables within your program, within your function, I should say. So in this example, we're going to call a function with two arguments. So we're going to put two arguments into the stack, and you can see them right there. We're going to create our stack frame. We can actually use the shorter version if you want. And we're going to create two local variables. Now the way that you create local variables is kind of the way that we backed up x4 and x5 in our demonstration, is that we want to create two 16-byte variables. So we're going to say subtract 32 from SP. So now notice how the stack pointer is pointing above the frame pointer. And I want to put 99 in the first one, and I want to put 88 in the second one. So what I'm going to do is I'm going to put 99 into x0, I'm going to put 88 into x1, and then I'm going to store x0 to the frame pointer, which is going to be right above the old frame pointer, and I'm going to store x1 into the frame pointer minus 16. Remember, the stack pointer moves down as we move up. So we put our two local variables in there. Pretty neat. You can also access your local variables, like I'm going to say load into x7 the frame pointer, which should put 99 into f7. You can see it right there. And then load plus 16, or I believe it was minus 16. Let's go back. So load into x8 the frame pointer minus 16. So x8 should have 88 in it. x7 should have 99, which they do. So when you access local variables, first of all, when you access local variables, you always use the frame pointer as the starting point. Local variables, you're always subtracting 16. Arguments, you're always adding. So that's an important concept to remember. Okay, when we're done doing whatever it is that we're doing, we destroy the stack. I still have local variables in there. It would have been a good idea to zero those out before I do that. And then the main function, when you return, it destroys the two arguments. I think what we should do is we should zero out our local variables before we end this function. And we're going to do that in the coding demo. So let's go ahead and take our add2 function. Let's copy it to another function that uses a local variables. Okay, so let's go ahead and take a look at using local variables. The first thing I'm going to do, just because I'm kind of lazy, I'm just going to copy my add2 function that I know is working. And I'm just going to go ahead and stick the number 2 at the end. I'm going to go up here and change this to add2 2. There it is. And now let's do something with some local variables. Now to keep things simple, I'm going to get rid of the backups of our registers. So let's get rid of those backups because we just want to create a local variable, and we can deal with backups later. So to create a local variable, what I'm going to do is I'm just going to say subtract sp16. So that creates our local variable. Now the local variable will be fp minus that value. So what I'm going to do is I'm going to say let's move 0. So I'm going to move into x0. And I want to zero out my local variable, so I'm going to then say store register x0 to fp, and that should store it in my first local variable. Now what we could do is we can make this a little more interesting. I'm going to make this equal 0x99. So let's put 99 into our local variable. Okay, so we do our addition. Now what I'm going to do is I want to add that 99. I want to add my local variable value to x0. So I'm going to say add to x0, x0 frame pointer, because frame pointer is pointing to our first we're going to add that to x0. So let's see how this builds. Okay, well you can't actually do that. Well, there's a couple of problems here. We're going to have to say, instead of move, we're going to say LRD. So let's fix that problem. And you can't actually do something directly to it like that. That's the frame pointer. So what we need to do is we need to say move into x1, or not move, let's say load register x1, our temporary value, and then we'll say let's add x1. And I believe that'll work. Now this will be useful because we'll be able to see how we grabbed our local variable that the frame pointer was pointing to. It should be equal to 99, and we put it into x1. So we should be able to see that on the debug. So let's go in there and debug it with our local variable. All right, let's get down to our call. We're putting 100 in there. There's our 2 arguments. Now we're in our call. So we're going to go ahead and set up our stack frame. Now what we're going to do is we're going to make room for our local variable. We're going to move 0 into x0, and we're going to put, actually that's not 0, that was actually negative, it was 99, right? So now we're going to put x0 into our local variable. Now it shows store x0 to x29, but that's okay. All right, so now we're down here on this code right here. So let's load our arguments into the registers. There's 100 into x4. There's 200 into x5. We're going to go ahead and move 0 into x0. We're going to add x4 and x5 together and put them into x0. There it is. Now what we're going to do is we're going to load into x1 our local variable from x29. And look at that. Here's our 99. So the 99 that we put in our local variable that was defined on the stack is now into x1. We're going to add that to our 300. It's now 399. And we're going to continue on, and our program ends. So a local variable is simply you subtract space from the stack, and you keep track of that position. That's FP. So what I'll do a lot of times is I'll say local variable number 1, FP. Let's say if I wanted to create 2 local variables, I'll say local variable number 2, that is in FP, comma, minus 16. Now, why do I do that? The reason I have this wrong over here. Let's get the syntax right. So why do I do that? Because as I'm coding down here, I want to know where are my local variables. And so I could do this with multiple variables. And this one here would be 32. So let's say if I wanted to move my sum into all 3 of my local variables. Yeah, so let's say if I wanted to do that, let's say after I add them, I want to say store register x0 to local variable number 2, that is FP, comma, asterisk minus 16. Store the sum into local variable number 2. And then I can do the same thing for number 3. I just come up here and say, oh, the 3rd local variable is 32. So I'll change that to 32. So my comments are helping me keep track of what the FP hashtag should be. Am I supposed to just say FP, FP minus 16, FP minus 32? And so that's what these 2 lines of code are doing because I just used my comments up here. All right, whew, a lot of coding, a lot of lectures. Stack frames, they're not really that difficult, but it's very easy to get off topic, to get off center. And that's why whenever I write functions, I always have a piece of paper in front of me and I take notes as I do it. So again, a stack frame, it uses the frame pointer and the stack pointer to keep track of the sub-stack that you have in your function. So the frame pointer is the starting point when accessing local variables or arguments. Arguments are always plus, the frame pointer plus, and local variable is always the frame pointer minus. So you can see that on the last bullet there. The frame pointer should never change. During the execution of your function, the frame pointer should always stay the same until the function ends and you destroy the stack frame. You'll also use multiples of 16 on a 64-bit application. You'll use multiples of 8 on a 32-bit application. So you have to keep track of that because of the way that the stack is organized. It must be aligned on a 16-byte word boundary on 64-bit apps and on an 8-byte word boundary on 32-bit apps. So it's just something else you have to keep in mind. Whew, man, that was a lot of work. But that's why the videos are great. You can go back and continue to review them until you get it just right. Hope to see you in our next video.